Okay, in this assignment, we're going to be looking at how we can calculate either speed or distance or time as long as we have two other variables that we can use to calculate. In other words, as long as we have two of those measurements, we can solve for a third one using math because they're all mathematically related. Okay, distance is all about how far something goes. Time is all about how long it takes to get there. So if you have the distance and the time that it takes for something to move, you can describe that object's speed, the rate at how it moves from place to place and how fast it's going. All right. Now you could also use the speed and the distance of an object to figure out how long it takes to get there. So if you know how fast something is moving and how far it's going to go, you can calculate how long it would take to get to that point. You could also use the speed and the time to figure out how far something can go. So if you know how fast something is traveling and how long it's going to travel that fast, you can predict how far it's going to be able to travel. So to do this, we have some equations that we can manipulate. This is the one that we use most often so far, where we have that the speed is equal to the distance divided by the time. And you can either write that with a little slash or a fraction bar, or you can do it with the division symbol. Okay, but we can also rearrange this algebraically. We're going to kind of go around the algebra method just to kind of save some time. So we're going to do some shortcuts. But you can get these different equations just by algebraically manipulating them. So if you multiply both sides by time on this equation, you can cancel that on the right, have it show up on the left, and you would get this equation here. You get that the distance on its own is equal to the speed times the time, which is this guy right here. You could also rearrange it to be something like this, okay? But again, we're going to kind of scooch around the algebra of it just to jump straight to figuring out which equation we need to use in that case. So in this first problem, when a hawk is hunting, it can dive to reach its prey 35 meters away in 0.65 seconds. We want to know the speed in meters per second of this hawk. So our 35 meters is the distance that our hawk can go. This 0.65 seconds is the time it takes for the hawk to travel 35 meters as it's diving. So we have the distance, we have the time. What we don't have is the speed. That's what we want to solve for. Okay, so we want an equation that has speed equals something and something, so we can calculate it. Okay, like this equation right here. Okay. Now, if you ever don't have these equations here, this little nifty triangle is something you might see that can help you figure things out. All you have to do is cover up the part that you're looking for. So in this case, we're looking for speed. So if I cover up the speed part of the triangle, what's left is what you need to calculate. Distance divided by time should give us the speed of the hawk. Okay, which is exactly what's up here too. So that's just two different ways you can kind of pick out the equation that you need. Okay, so you can either say, hey, I've got this equation right here where it says S equals, or you can say, I'm going to cover up the part that I'm missing, and whatever is left is what I'm going to do to calculate my answer. So let's do that. Whichever method you use to get the right equation, we're going to take the speed is going to be equal to our distance divided by our time. So distance on top. Our distance is 35 meters. Our time is 0.65 seconds. Okay, now if I plug this into a calculator, I should be able to figure out the speed in meters per second. Now, let's see, my mental math is definitely not good enough for this, so I'm going to have to reach over here and grab my calculator. So I take 35 divided by 0.65, and what I get is about 53.85 or so. All right, my unit is going to be meters per second, or meters slash seconds, kind of like miles per hour. Okay, and that's my speed. That's my answer. Okay, So we've done some problems like this before, where we can calculate the speed or velocity by taking the distance divided by the time. So hopefully that's not super new. But what is going to be a little new is that we can go in other directions with this, where we can figure out the distance or figure out the time given some different information. So let's look at some of those examples too. Okay, a car drives down a road at 48 kilometers per hour, okay, which is about 30 miles an hour if you want to have kind of a reference point here. So if the car continues at that speed for 48 kilometers per hour, and it's going for 0.5 hours, how many kilometers will the car travel? That's what we want to figure out. So let's break down what information we have. Kilometers is just a longer way of measuring distance. So this is going to be our distance here. Okay. Per hour, okay, it's telling us how far it travels per the amount of time it takes to get there. So this together, this 48 kilometers per hour, is the speed. They're already giving us the speed. Okay. So at this speed of 48 kilometers per hour, if this car is traveling for half an hour for 0.5 hours, we want to know how many kilometers the car is going to travel, what distance it can cover. Okay, so in this case, we're actually solving for the distance. We want d equals, and then something times something, or something divided by something. We want d equals in our equation. Okay, so again, you can either find an equation that fits best, like, hey, this one's looking pretty good, d equals s times t, or I could cover up distance here on my triangle, and what I have left is s times t here. Works the same way, either way, just pick whichever method works best for you. So in order to solve for the distance, I'm going to say that d is equal to my speed, which is 48 kilometers per hour, 48 kilometers per hour. Okay, that's going to be times the number of hours the car is traveling, which is 0.5 hours. Okay, so again, you can plug this into a calculator. 48 times 0.5 is going to be about 24. And since we're calculating distance, this is going to be kilometers. Okay, now see that this works for any measurement of distance and time. This doesn't just have to be for meters per second. It can be kilometers per hour. It could be miles per hour. This equation will fit any type of distance and time and can give you a speed for that distance per time. Okay, so in this case, we can solve for a number of kilometers, not just meters or something like that. The equation works with whatever units you put in as long as you've got distance and time and speed involved. Okay, so this is how far the car can travel. If it's only going for half an hour, it can only travel half of that 48. Okay, let's look at another example. A baseball thrown by a major league pitcher moves at 44.7 meters per second. Okay, so right off the bat, because it's a baseball question. This 44.7 meters per second is a speed. Okay, it's a distance per time. So we're given the speed again in this case. Okay, and this time we're also given the distance. Okay, the ball is going to move about 18.44 meters to get from the pitching mound to home plate. How long will it take in seconds for the baseball to travel from the pitcher to the batter? So we want to figure out time. Okay, how long will it take? Okay, in seconds. We're searching for time. So we want time equals in our equation. So looking at my options here, this guy, t equals d divided by s, is going to be my best option. Or, again, if I want to use the triangle, I can cover up the stuff with t. And what I have left is d divided by s, my distance divided by my speed. All right, so let's plug that in. If I take t equals, all right, my distance is 18.44 meters. Ooh, and you know what? Actually, I'm going to do this a little bit different this time. 18.44 meters. And I'm going to write this with a division sign this time instead of doing the fraction bar, just so you can kind of see it two different ways. So divided by my speed, which is 44.7 meters. per second. Here we go. I should get my time in seconds. Okay, or whatever unit I'm using for time. In this case, it's seconds. Okay, so let's plug this into a calculator. I'm taking my 18.44 divided by 44.7. And what I get is about 0.413-ish. 0.413. Now, if you don't get exactly 0.413, it's probably because of rounding in your calculator. When you get some really weird numbers that don't come out to like something nice and clean and whole, that's okay. Just round as best as you can. On multiple choice, you'll just have to pick the closest answer. Only write in my S for seconds. Multiple choice, you just pick the closest answer, or if it's open-ended, I know what to expect, so I'm looking for kind of like the ballpark answer. It's a ballpark because it's again a baseball question. Man, I'm batting 1,000. Hey, man, that's 3 for 3. Call that a home run. All right, I'm done with the baseball things. So your 0.413 seconds is how long the ball will take to get from place to place. And if you didn't get exactly 0.413, like on my calculator, it's like 0.41252796 or something like that. That's okay. Oh, my dog is dreaming. So if you hear any like little woofs in the background, it's because he's dreaming, kicking his little feet. It's pretty cute. Okay. Let's do another example. All right. Numbers 4, 5, and 6 are all pretty similar to the ones that we've already done. Okay, but I step up the difficulty a little bit. So in number 4, I don't lay it out quite so cleanly of what the distance and the time is, so I don't have it like, with parentheses and stuff around it. Okay, so in number 4, okay, fastest football player could run 100 meters. That's a distance. In 9.69 seconds, that's a time. Okay, so we could solve for speed by using one of these equations where you have S equals. Okay, so S equals. Okay, and then you're going to use one of these equations, which I think you guys can figure out. I have faith in you. Let's see at number 5, a sonic boom. In this case, we're given this speed in meters per second. So we're already given a speed. And we're given a time down here. Okay, it doesn't really say the time is 10 seconds, but seconds is a unit of time. So again, you have to kind of have a careful eye for these kinds of problems. So in this case, we're looking for how far this is going to travel, this jet. So you'll want D equals something divided by something or something times something. So again, make sure you pick the right equation for that. And make sure you're careful about what goes on top and bottom when you divide these out. So let's look at this one on number 6. Okay, number 6 is asking how long will it take? Okay, which is going to be some amount of time. In this case, it's probably going to be seconds because our speed is dealing in meters per second. So you're going to have time equals, and our time equals equation is going to look like this guy, where it's D for our distance divided by our speed, S. If you take your speed divided by your distance instead of your distance divided by your speed, you get a different answer. So be careful about which one you put first. Okay? So that's my kind of hint to you. I also want to tell you, do not let these big numbers scare you. Okay? This is like a really, really, really intensely fast speed. This is the fastest physical speed that something can actually have in our universe. It's the speed of light. Can't get really any faster than that. This also gives us a distance. Okay, and this is a huge amount of distance that can be covered here. Okay, so do not let those numbers freak you out and scare you. Again, use a calculator. If you're on like a phone calculator, sometimes if you type in too many numbers, it kind of runs out of room. You might have to turn it sideways to kind of get your calculator to have a bigger size, and then you can type in more numbers. But usually if you're on like a computer calculator or like a physical calculator, it can handle a lot of numbers. So it should be able to handle those. Okay, so I think you guys can figure out 4, 5, and 6, and I think you guys can figure out number 7. But I want to do that one together as an example too, because it throws a lot at you, and so I just want to walk through and show that it's really not any different from the stuff we have been doing. It just adds a couple extra steps. Okay, so in this last problem, a roller coaster goes through many ups and downs. At one point in the ride, the roller coaster drops from its highest point. Okay, this delta y is just saying, oops, that should just be a y. I. So let me get that out of there. Okay, yi is going to be 70 meters. Okay, where this I just stands for initial. It's the initial height. We usually use y to talk about the vertical distance, like on like the axis of a graph that goes vertical. So our coaster starts 70 meters above the ground, and then it drops down to about 4 meters, which we're calling our YF, which is our final height above the ground. Okay, our final vertical distance. This drop happens near the end of the ride. So if you start the ride and start a timer at the same time, this happens at an initial time of 110 seconds and stops at about 112.5 seconds. Okay, so that seems like a lot of numbers. It's like we have two distances here, there, and there. We have two times here and here. Our goal is going to be to calculate the velocity of the roller coaster during this drop. Okay, so this is during a segment of time. In order to do this, we're going to take the displacement, which is this delta y, okay, or I guess delta x, but I forgot to just change this. So let's do this. Delta, let me see if I can just write over it. Delta y. There we go. Okay, delta y. Okay, the change in the vertical distance. All right, and we've also got the change in time for so what period of time this is happening in. Okay, so instead of just having a distance of this is how far the coaster goes, we're saying how far did it go from here to here? Okay, from final minus to initial. So our final point of the roller coaster, where it ends up at, is 4 meters. So our change in our vertical distance, aka the displacement vertically, is going to be 4 meters minus 70 meters, where we started. Okay, that's our final minus our initial, our final minus our initial. Okay, and this should give us the difference between those, how far the roller coaster traveled between that 70 meter point and that 40 or 4 meter point. Okay, so if you plug this into a calculator, you get 66 meters, but it's negative. You get negative 66 meters, and it kind of looks like we did something wrong, but we didn't. A change in something also can kind of include whether something is increasing or decreasing, or whether it's going left or right, up or down, higher or lower. It gives us that extra bit of information. So this is saying that we are specifically not just going 66 meters, period. We're going 66 meters downwards. Okay, this negative number means that our coaster is going downwards. If our roller coaster was going upwards, then our change in our height is going to be positive. You'd end up at a higher point at your final point, and then so when you take a higher number minus a lower number, you're going to get a positive number. So the fact that we get this change to be negative means that we're going downwards. Okay, it just gives us a little bit of extra information. It's not a mistake. So let's look at B, which is how long it takes for the roller coaster to go through that drop, going down 66 meters. Okay, so kind of like the change in height, this change in time is going to be the final measurement minus the initial measurement to say how long it took from 110 seconds to 112.5 seconds. So our final point where we stop the stopwatch is going to be 112.5 seconds minus where we started at, which was 110 seconds. So if you plug this into a calculator, you should get about 2.5 seconds. Okay, this one comes out positive. You can't really have time going backwards instead of forward, so your time should always come out positive when you're doing a change in time. But just to make sure. Okay. The time it takes is 2.5 seconds. The last thing we're going to do is calculate the velocity of the roller coaster. Okay. Where the velocity is basically the speed, but with a specific direction, like going downwards. Okay. So if our roller coaster is going 66 meters downwards, that's what the negative means, going downwards, and it takes 2.5 seconds to go downwards, that can tell us how fast the roller coaster is going. Okay, so our equations for velocity are basically the same as speed. It's just we call velocity, instead of the speed. Instead of using distance, we use that displacement, that change in height, and instead of just time, we use a change in time. So this equation right here looks to be pretty fitting. And if you were to kind of get rid of this on the triangle here, you'd have the same thing. Your delta y divided by delta t gives you your v, or your velocity is calculated by taking your change in height divided by your change in time. So let's do that. So our velocity, v, is going to be equal to, all right, and then we're going to have our change in height, which we calculated to be negative 66 meters. All right. Divided by our change in time, which was 2.5. Ooh, that didn't turn out too well. Let's try that again. There we go. 2.5 seconds. Plug this into a calculator. So 66 divided by 2.5 is 26.4 meters per second. So if our roller coaster is dropping 66 meters downwards in 2.5 seconds, that means it's traveling at a velocity of 26.4 meters per second. And specifically, this also comes out negative. So that means it's going downwards. Okay. Again, we get that extra bit of information. We are told the direction that this is moving in. Okay. Not just that it's going this fast, but specifically this fast downwards. So the speed of the roller coaster is going to be negative 26.4 meters per second, which means it's going downwards at that rate. Okay, so hopefully that helps, and hopefully the other problems that we didn't totally walk through together, which I believe was 4, 5, and 6. Hopefully those won't be too bad. I have faith in you guys, and that's it for this video.